Thanks very much, and welcome to this webinar on digital analytics. Basically, what we want to try to do today is to explain some of the technologies that we've been using in other industries and how these can be modified for use in the water industry. A lot of the techniques that we've developed so far and will be described today have been developed for the oil and gas industries. But there's no reason why they can't be transferred into the water industry. So just as a way of introduction, my name is Carl Wordsworth, and as John said, I'm head of water, and I've worked at Toughsud now for just over 3 years. I've got 25 years experience in fluid engineering, research and development, mainly in the oil and gas and water industries. I worked for many years for a small oil and gas product development company, where I actually developed a bulk oil water separator. And I've also spent many years as a third-party contract research, working for an organisation that companies come to in order to develop the research that they need to develop their products. So I've got a lot of experience with fluid engineering, test rig design, and basic R&D into fluid-related projects. In this webinar, I'm going to discuss several things. Firstly, why is water so important, and how by reducing leakage we may be able to meet the future water demands that we're going to require for the future. I'll also touch on what data analysis tools NEL have looked at and how these can be adapted for the water industry. I'll then go through a series of case studies that shows how NEL have developed the various digital tools, explain how these have been used in practice, and then how these can be modified to be used for water. Then I'll go on to explain what work needs to be undertaken to develop a fully functional software suite that can be used by the water industry to locate and predict leakage in water networks. So firstly, why is water so important? Well, water sustains life. 2/3 of our body is made up of water, and our brains are at least 85% water. The average person cannot live for more than 3 days without water. It's key to biodiversity. We can only truly have biodiversity if we look after the lakes, rivers, and the fresh water that supply life. Water is required for economic growth. According to a 2016 UN report, an estimated 3 out of 4 jobs that make up the global workforce are either heavily or moderately dependent on water. It enhances life, and we rely on water for everything we eat, drink, for washing ourselves and our clothes, and it helps to create the energy we need for heat and light. It's essential for the products we enjoy, the rivers, fields, forests, and the beaches that we love. Without water, life as we know it would be impossible. Water, however, is a finite substance. The amount of water that we have in the water cycle is unchanging. How it is stored can, of course, change. It can be a liquid, ice, snow, etc. But the key point is we cannot magically put more H2O into the water cycle. If you look at the map of the world, it may seem we have lots of water available. After all, water covers 70% of our planet, but only 3% of this is freshwater. And of this, 2/3 are either frozen or unavailable for use. So you can see that the actual amount of fresh water that we have in the environment is quite limited. If you look at the figure on the right there, this is from data from the University Corporation for Atmospheric Research, and it shows that due to climate change, droughts are going to be more common. The figure shown here, the areas in red and dark colours, represent drought conditions. So by 2030, it's expected that large portions of the Earth could be in drought, meaning we need to look after the finite water resource we have. And therefore, this also includes reducing the water that's lost to the environment. By 2030, it's estimated that the world population is expected to rise to 8.3 billion people, and then on up to 11.2 billion by the end of the century. All this will put extra demands on freshwater requirements. Indeed, it's predicted water demand in some industries will grow dramatically. For instance, by 2050, it is predicted water demand by manufacturing will increase by 400% compared to the 2000 levels. Therefore, reducing leakage from water pipes will allow us to reduce abstractions and help ensure we have enough water to meet future demands. It's been estimated that if global leakage levels could be reduced by a third, this would be sufficient to supply 800 million people with fresh water. And this would come on with the financial benefit of about $13 billion per year. So to meet the future demands, action is required now. It will be necessary to reduce the demand and increase supply to meet future freshwater requirements. But there will be enough water to meet the world's growing needs, but only by dramatically changing the way water is used, managed and shared. This map shows some of the global estimated unaccounted for water levels that have been estimated in 2018. Unaccounted for water is any water that is being produced and is lost before it reaches the customer. The water can be lost in a number of ways: through leakage, through metering inaccuracies, through unbilled consumption, or even theft. It can be seen from the map there are large variations in the levels of unaccounted for water around the world, with very low values of only 0.3 billion metres cubed per year observed in Australia and New Zealand, to much higher levels of 25.2 billion metres cubed per year in Latin America and the Caribbean. The lowest values that are observed from Australia and New Zealand show that a huge amount of effort has been placed on water loss reduction by Australia and New Zealand over recent years in order to be able to better cope with longer drought conditions. Therefore, their leakage levels are really quite small. And this shows just what can be done regarding reducing the amount of unaccounted for water if there is a will to undertake the research and development into this area. If we look at the UK, it's been estimated that within the UK water network, 75% of water going into the system passes through flow meters of 500 millimetres or greater, and 25% through meters of 1,000 millimetres or greater. So this represents about 11.25 billion litres a day going in 500 millimetre flow meters and 3.75 billion litres per day in the larger pipe diameters. Now, although the number of these very large diameter meters is very small, the proportion of water they're measuring is really quite large. For example, one water company reported that they only have 8 of the meters of 1,000 millimetres or greater, but 25% of their daily flow passes through these meters. This represents approximately 500 million litres of water per day passing through 8 of these meters of 1,000 millimetres or more. By using these large diameter flow meters, you can see that even if there's a very small error in the meter uncertainty, this could result in the flow measurement reading being quite wrong, and could result in large volumes of water being missing, which could be misreported as leakage. So therefore, it's vitally important that we recognise the difference between actual leakage and the errors associated with measurement uncertainty of the very large flow meters that are used in these distribution networks. In the last few years, the availability of inexpensive computing power and measurement databases has enabled the development of powerful data analysis techniques that allow metering networks to be monitored daily. Such techniques can give operators details about meter performance and leakage and are much more effective than the traditional water balance calculation over the distribution network. I'll cover a range of these techniques in this presentation and show, using case studies, how these are being used in practice and how we can actually modify these for use in the water industry. So if we now go on to some of the digital services that are offered by Tussud, we've undertaken a large amount of research looking at using emerging data science techniques to help make better use of the information gathered by modern flow meters. Based on a huge database of testing, covering a range of different flow meters under a range of different conditions, we've developed a range of software tools to help develop things such as data visualization tools, looking at evaluating historical data, the use of flow meter diagnostic data, for the development of fault diagnostics for the flow meters. And this flow meter diagnostic data is the data that's generated by most modern flow meters that's generated in the background and is on top of the information that's generated on the actual flow itself. We also look at remote monitoring, looking at undertaking a health assessment of the flow meter, and also predictive analysis by the use of machine learning tools to look at the remaining useful life of the device. So we've covered a range of different projects that have been undertaken looking at a range of these different tools. And as I said, I've got a number of case studies to show you to explain some of these techniques that we think can be used for the water industry. As manufacturers of instrumentation continue to embrace digital technologies in place of traditional analog electrical signals as a means of communicating data, end users can now be faced with interpreting screens of data with multiple process variables, which, as well as providing the primary variable of interest, i.e. the flow rate, the pressure, the temperature, also include device-specific diagnostic values. Unless these values are reviewed by a subject expert, these can either be meaningless or misinterpreted. In many cases, the usefulness of this diagnostic variable can only be very application-specific, and different stimuli can cause similar responses in more than one variable. Using our flow laboratories, we have conducted experimentation on specific flow meters, which can intentionally, and we've intentionally exposed them to undesirable operating conditions while logging all the available diagnostic data from the devices. Through detailed analysis and data-driven modelling, our digital services team were able to then identify subtle and hidden correlations between the various digital process variables and the physical effects experienced by the meter. By combining the facilities of the UK's national standard for flow measurement with emerging data science techniques, we have been able to provide end users with a means of interpreting meter-specific diagnostic data and relating the response on the said data to specific operating conditions. The experiments and data science techniques utilised to produce the above results can be deployed to address specific end-user requirements on a case-by-case basis, as well as form the foundation of a much larger condition-based monitoring system. These approaches can also be used to provide the back-end functionality to a much simpler interface that simply tells the user when the prevailing fault, what the prevailing fault condition is. The data science techniques developed by TUFSUD are able to take data from a range of different areas, including pressure transmitters, temperature transmitters, flow meters, valve positioners, pump feedback indicators. The software is also able to use multiple diagnostic variables, such as those generated by modern electronic flow meters, to develop correlations that would generally be too complex for a human to undertake manually. It's also possible to use a range of different signals, both analog and digital. We have the skills to understand the importance of differentiating between an analog and a digital signal when developing machine learning tools. For example, electrical noise and an analog signal versus data like from a digital signal, and how that cascades through the model. We can also take data from PLCs. And because our digital team is made up of a number of different engineers, ranging from control and instrumentation, we have data science engineers and mathematicians, we are able to fully tackle the problem and not just undertake blind modelling. So some of the benefits to the clients, it can provide fresh insights and measurements of their system and data logging capabilities. This data-driven intelligence will help clients to monitor asset performance in real time, increase asset utilization, reduce unplanned downtime, reduce maintenance costs, optimize maintenance intervals of assets, improve operational safety, reduce overall operational costs, and improve energy efficiency. So you can see there are a number of benefits to using these techniques on both historical and live data. What I'll do now is talk about some of the case studies of some of the work that we've done in the past and how these can be modified to be used in the water industry. So initially, condition-based monitoring can be used to determine the health of a flow meter, and can also be used to monitor the calibration requirements of the device, to understand if moving from a time-based calibration approach to a more dynamic calibration approach can be used. By making use of the diagnostic data that most modern flow meters generate, it is possible to use data analytics to determine the health and performance of the flow meter. Currently, we've undertaken studies looking at both Coriolis meters and ultrasonic flow meters, but it's entirely possible to transfer the knowledge gained from this to do the same for electromagnetic flow meters, the main flow meter of use in the water industry. And this is the next stage of the development of the condition-based monitoring that we want to undertake to transfer the knowledge that we've gained in the oil and gas industry and transfer this to the water industry. So firstly, we looked at ultrasonic flow meters. Most modern ultrasonic flow meters output vast quantities of digital data in the form of individual process values, commonly referred to as diagnostics. In theory, this information can be used to determine meter performance, as well as infer process and installation conditions. For example, any potential flow measurement errors resulting from incorrect installation, particle deposition, if you've got wax buildup on the transducer port, for example, or the presence of an unexpected thickened fluid phase, usually manifest as measurement errors. However, without extensive field experience, it can be challenging for end users to interpret these values and relate them to specific sources of error due to the fact that the same diagnostic drift of a variable may be observed for multiple scenarios. We therefore cannot rely on simple trending and alarming on one specific variable in order to obtain reliable and actionable information. We need to look at a combination of digital variables and their associated response to a given scenario in order to evaluate the system, which in turn renders basic human observation largely subjective and unreliable, hence the need to move to the computerized data analytics that we talk about here. This shows you a series of different variables that we've actually programmed into the software using a machine learning algorithm, and using our flow laboratories. We've conducted experimentation on multiple brands of ultrasonic meter, in which we intentionally expose them to undesirable operating conditions while logging the available diagnostic values obtained via the meter's fieldbus port. Through data-driven modeling techniques, our digital services team were able to identify hidden correlations between the various digital process values, and were able to build a tool which can identify specific fault conditions and alert end users via simple graphic interfaces. The graphs shown in the slide above show the probability of the prediction from the software of the type of error the meter is experiencing. From the numbers shown in the graph, it can be seen that the software predicts the type of error that is being observed with a high degree of accuracy. This allows the performance of ultrasonic flow meters to be examined by examining the live flow meter diagnostic data, and therefore we can identify any issues with the flow meter or any of the issues that we've actually programmed into the machine learning tool. The output of this project has demonstrated the potential for end users to increase operational efficiency through harnessing the data. This data is already available to them through most standard ultrasonic transmitters, and equipped with the ability to identify a specific fault, there is no longer a need for end users to shut down production, remove the meter from a pipeline, and conduct multiple diagnostic tests before the solution can be found. This can be done online with live data using these machine learning tools. This in turn has significant long-term cost-saving implications and the potential to increase plant operation efficiency. The tool can be applied to both historical data sets and live stream data. Anomaly detection can go on to inform more detailed condition-based monitoring systems, i.e. not just detecting anomalies, but identifying specific faults unique to a given operation. This is another case study that we've looked at, and this is looking at condition-based calibration, where we use the diagnostic data that the flow meters generate to try and examine the calibration period required for that flow meter. So as we said, most modern electronic flow meters generate large quantities of diagnostic data on top of the flow rates that are measured. This data can be used with data science techniques to help train software to recognise when there is an issue with the performance of the flow meter. The case study shown here was undertaken for Coriolis meters, and as we already mentioned, we've also undertaken work for ultrasonic flow meters, but the techniques developed here would be as relevant for modern electromagnetic flow meters that are generally used within the water industry. By implementing a condition-based calibration schedule, end users, in theory, have the ability to reduce costs through a more dynamic operating pattern. This is achieved by continuous monitoring of key digital diagnostic and standard instrument outputs, which are then compared to known baseline conditions. In addition, with enough historical data, condition-based calibration systems can be used to predict device calibration drift over time and correct for this. However, in reality, the performance of a given meter will vary between manufacturers, as will the availability and the relevance of the digital diagnostic data. There's also a great number of physical factors to account for. For example, in a pipe network, there will almost certainly be pipe bends and valves upstream of the device, as well as pressure and temperature effects, which are known to affect the performance of Coriolis meters. And all of these can influence the performance of flow meters to differing extents depending on the type of the flow meter and the manufacturer. We undertook a huge amount of work looking at using Coriolis meters and introduced a range of errors into them to investigate the flow meter diagnostic data and how the various diagnostic terms vary depending on the induced error. By making use of this data, it's possible to develop correlations based on the variables under each scenario. This then allowed a model to be developed that would automatically determine possible failure conditions based on the diagnostic data for the flow meter, By continuously monitoring live diagnostic data from the meter, it is then possible to use this data to predict the flow meter calibration drift over time, which allows a move from a time-based calibration approach to a more dynamic calibration approach. The benefit of this work showed that by continuous monitoring of the diagnostic data and the standard instrument outputs, it is possible to predict the flow meter calibration drift over time, thus allowing a reduction in costs by making use of a more dynamic operating pattern. This just shows another example of the same thing, where we're looking at a condition-based calibration. Again, this is for a Coriolis mass flow meter. And typically, the Coriolis meter would be calibrated on a regular periodic calibration, probably yearly. However, this periodic calibration does not take into account whether the flow meter actually requires to be calibrated or not, and so is a safe but expensive option. Obviously, calibrating these flow meters is quite expensive. You have to take them out to your test facility, send them away to a calibration facility, have them calibrated, and then reinstall them. So it can be quite a lengthy and expensive process. We know that Coriolis meters are one of the new modern flow meters that generate vast quantities of diagnostic data. And by getting access to this data and using data analytics and machine learning techniques, we can then use this data to assess the performance and health of the flow meter and the health of the system. The condition-based software analyzes diagnostic data generated by the flow meter and can detect when anomalies occur. These anomalies can then trigger a signal to the operator to recommend the flow meter to be recalibrated. What this means is that the calibration period can be extended, saving time and money, and you only actually calibrate the device when it actually is required to be calibrated. The second tool that I'd like to talk to you today about is something called data validation and reconciliation. One cost-effective way of increasing confidence in flow meter data accuracy is to use a technique known as data validation and reconciliation. And this is a statistical method that may be used to evaluate the quality of flow measurement data from all types of systems. Data validation and reconciliation can be applied to many different types of industrial plant, from simple systems consisting of only a few measurements to complicated systems with several hundred. Due to the large number of calculations involved, data reconciliation is particularly suited to software application. The basic function of the software is twofold. Firstly, to provide users with more reliable and accurate data, and to alert operators to instrumentation readings outside uncertainty bands. The first stage in the reconciliation process is to select a set of measurements that is to be validated. For reconciliation to be successful, the system must contain a degree of data redundancy. That is, some of the measurements may be determined in more than one way. This normally will be by direct measurements and by one or more balances involved in other dependent measurements. You can see we've got an example of a water network here. So we've split the system up into a series of nodes identified by the numbers 1 to 8. If we look at node 1, we can see that the inlet flow is identified as being 71.55. This then passes into node 1, where 3 further flow meters measure the flow split from that node. Assuming conservation of mass, the inlet flow to node 1 should equal the outlet flow. In the case shown here, we can see that this is not the case. The inlet flow for node 1 is measured at 71.55, and the outlet flow is measured at 64.66. Therefore, there is an issue. The next stage is to describe how each measurement depends on others in the system. This involves the application of energy conservation equations to the full set of measurements. For flowing pipe networks, this is particularly simple, and the process reduces the formulation to a set of mass balances around the nodes that are shown in the previous slide. And this is what you can see in the table shown here. For the example shown in node 1, the equation of conservation mass is equal to M1, which is the inlet flow, equals the outlet flows of M2 plus M3 plus M4. This therefore allows an estimate of the difference in the inlet and outlet of the nodes to be identified. However, these balances only tell you so much. It is then necessary to undertake a series of reconciliation calculations using linear regression techniques that I won't go into here. The validation process itself involves calculating adjustments to the measured values to make the amended values obey the conservation equations. This is done by minimizing the squares of the uncertainties. This is similar to performing a least squares fit for the data points on a graph. And for each measurement, the size of adjustment required is compared with the unassigned uncertainty through a calculation of the quality index. The quality index values are the figures you can see indicated on this network, shown on the right-hand side. Generally, if the value of this quality index exceeds 2 for a 95% confidence level, then the measurement should be scrutinized. Commonly, the quality index for an individual measurement is plotted against time, as you can see from the graph on the right. In this way, reconciliation can act as an early warning system against instrumentation drifting out of calibration. You can see how the quality index changes over time. Once the meters with the highest quality index has been identified, these meters should then be investigated and physically inspected to determine if there are any faults with the flow meter. In the case shown here, meter M3 was found to have the highest quality index value. This meter was inspected and was found to have a fault. This fault was then fixed, and the data validation and reconciliation process was run again, with the results shown on the right-hand side. Once again, M3 still has the highest value of the quality index. This suggests that there may be a leak in that line. After inspection, a leak was found, it was detected and repaired, and the data validation and reconciliation process was run again. This time, the quality indices that were found to be very low. This shows how data validation and reconciliation can be used to help locate leaks in the network. If this tool is combined with the condition-based monitoring software, this will allow additional data on the health and performance of the flow meter to be incorporated into data validation and reconciliation, allowing a better assessment of the flow within the network. Data validation and reconciliation tells us that it can be used as a diagnostic tool to pinpoint exactly where meters are operating outside their uncertainty bands. This may indicate that operators have made correct assumptions about the uncertainty of the meter. This can be changed and the reconciliation rerun with a new value. Alternatively, it may mean the meter is drifting out of calibration or that a fault is developed. Either way, the ability of the technique to highlight anomalies will allow operators to target maintenance of specific equipment with obvious financial benefits. Data reconciliation is not magic. It does not introduce new data that is not already there. What it does is allow the operators of networks to make the most of the data that they have with the accompanying financial and operational benefits. If we now move to the final case study that I'd like to talk to you about, and that is using machine learning to detect fault prediction and try and estimate useful life of equipment. The first case study covers a fuel bunkering system that we looked at. And fuel bunkering is the process of transferring fuel from a storage vessel, typically located at a shipping port or within a mobile tanker ship, to ensure that the correct quantity of fluid is delivered and thus ensure all financial transactions are accurate and traceable. Typically, a mass flow meter such as a Coriolis is installed in series with the fuel transfer pipe, and this is used to actually measure the amount of fuel transferred. However, the fuel bunkering industry has recently seen a rise in fraudulent activity whereby the perpetrator seeks to undermine the Coriolis meter's measurement integrity by attaching a magnet to the outer case of the device. By doing this, it is possible to disrupt the inlet or outlet phase shift sensor readings in the flow meter and thus distort the meter's mass flow calculation by causing an under or over reading, benefiting either the buyer or the seller. To train a model to detect criminal activity such as fuel theft, one needs real data where the fraudulent activity is present within the variables logged. However, such data sets are inherently illegal to produce in real life, and therefore there are practical limitations in recreating such conditions in controlled environments such as a flow measurement laboratory. To account for this, something called synthetic data generation can be used and has been shown to be a viable solution for addressing such data availability issues in sectors such as healthcare, banking, and manufacturing. Synthetic data are data that are artificially created by different algorithms to mirror the statistical properties of real data with the aim of protecting privacy, testing systems, testing algorithm performance, and generating training data for data-driven algorithms. For instance, when there are limited observations within a data set for a specific real-world event, or when collecting real data for the training of a machine learning algorithm is expensive, then a diverse and valid set of data can be generated using this synthetic data generation tool. The model that we've described here in this case study was built and trained using synthetically generated data, and it displayed the capability to detect the presence of a magnet in a real field data set. Another system that we've looked at is looking at the flow meter useful life in an erosive atmosphere. In hydrocarbon recovery, it's inevitable that sand will be present within the fluid passing through flow meters. Under such conditions, the meter's internal components will be eroded away and critical parts may be also damaged. This would therefore incur significant repair costs, as well as the potential for invalid device measurements after a given period of exposure. It's not always possible to perform a visual inspection of devices installed in the field, and even in cases where this is possible, a physical intervention is required, and end users rely on subjective interpretation of the impact of erosion on their meter performance. We have analysed our historical erosion data sets, which were initially obtained using our erosion test facility, and this study focused on 2 different brands of Coriolis meter and 1 turbine meter. The meters were exposed to the same erosive conditions, while diagnostic data was logged from the meter digital registers. Our digital services team then applied advanced mathematical and statistical modelling techniques to the data sets, and in doing so developed a tool which was capable of predicting the life expectancy of the flow meters after exposure to the sand erosion. Machine learning algorithms were then built to predict the level of sand concentration present within the fluid based on the response of the meter's digital outputs. By applying these new modelling techniques to a data set that until now had resided on a server unopened for 5 years, we've extracted new information relating to the performance of the meters. We've provided a means of predicting flow meter life expectancy in harsh environments without the need for removing and inspecting the meter by hand. Furthermore, by analysing correlations between diagnostic data values, it is possible to determine the concentration of sand within a flow system, essentially creating a sand flow measurement meter. Such diagnostic tools are becoming ever more critical to production and metering operations, where reduced downtime and overall costs are a key focus for the end user. Predictive analysis machine learning tools have previously been used by us to look at a range of different subjects, including fuel bunkering and the predicted life of flow meters. This technique that has been generated in the previous cases can be used to help predict leakage in water mains. To do this will require more information than just generated by flow meters. By looking at the pressure measurement that may be present on your networks, it should be possible to determine a telltale trigger signal from previous bursts or leaks that could be used to predict when a leakage event may be happened. If pressure instrumentation is not readily available on your networks, it will be possible to add this instrumentation to start collecting data. By allowing NEL access to your data sets of any networks where leakage or bursts have occurred previously, it will be possible for us to determine if there is sufficient data to be able to train the machine learning tool to recognise when a burst is likely to occur in the future. As we've already stated, if the historical data on these systems do not exist, it may be possible for us to generate synthetic data that could be used to train the machine learning software, as was explained within the fuel bunkering case study. This would greatly reduce the amount of real data that would be required in order to help produce the leak prediction software. So, what next? So, we've discussed 3 different software tools: the condition-based monitoring calibration tool, the data validation and reconciliation, and the fault prediction using machine learning. By combining the 3 software tools that have been described in this presentation, it will be possible to develop a complete software tool for the water industry that will be possible to provide a health check on your flow meters, as well as locate and predict potential future leakage events. The software will take the condition-based monitoring work and apply this to the electromagnetic flow meters. This will allow the performance and health of the flow meters in the network to be determined. By combining this with data validation and reconciliation software, it will be possible to determine if any leaks identified in the network mass balances are actual leaks, or whether they may be down to measurement uncertainty of the flow meters. And by performing the CBM on the flow meters on the network, we can then identify the health and the performance of your flow meters. By making use of historical data and using machine learning tools, it will be possible to actually predict where leakage is likely to occur in the water networks. This will require more information than just available from the flow meters, and will require data from pressure measurements in the network. The objective is to use machine learning to allow the software package to identify potential trigger signals from the instrumentation placed in the network. And by looking at historical data where known bursts or leaks have occurred, the signals from the instrumentation can then be used to train machine learning software to recognise these trigger signals and then provide an alert when these signals are observed in live data, thus predicting when likely bursts or leaks may occur. This will give the water companies advanced knowledge on when and where potential problems may occur and allow an inspection of the pipe to be undertaken before a burst or leak develops. The individual software packages and techniques described in this presentation have all been developed for the oil and gas industry. These now need to be modified for the water industry. This may require some physical testing to be undertaken to baseline the differences in performance between electromagnetic and Coriolis flow meters and ultrasonic flow meters, and will require historical data on water networks where known bursts or leaks have occurred to train the machine learning programs. But the techniques and methodologies for undertaking this work have all been identified and constructed previously. Optimizing data utilization is an operational imperative, especially to water companies under environmental, regulatory, and resource pressure. Failure to protect significant metering investments by not complementing it with modern, cost-effective data analysis techniques risk increased capital and operational expenditure through poor targeting of effort. Smart metering and the network analysis, therefore, will have to be used together to achieve the improvements necessary to meet the challenges facing the water industry today. This will give water companies much more confidence in the data, and so in their investment decisions and operational expenditure levels. The application of these techniques, along with recent advances in electronics and computing power, will give water companies the tools to meet the challenges facing them in the 21st century. Therefore, we are looking for water company partners to be able to work with us in developing a complete leak location and prediction digital solution for the water industry. If this is of interest to you or your company, please don't hesitate to contact me. My contact details are given in this slide here, and we will be happy to discuss the potential of this work with you in more detail. That's the end of my presentation. Just to talk about some forthcoming events, there's the Global Flow Measurement Workshop in October in Aberdeen. So, are there any questions on anything that I've presented today? John, are you there?
There we go. That's us. Right, Carl, thanks for that. We've got a few questions. Let's just... okay, right. In the webinar, you mentioned case studies looking at Coriolis and ultrasonic meters. Have you undertaken any work on electromagnetic meters?
We've undertaken a huge amount of work on electromagnetic flow meters in the past, but what we will need to do is we will need to undertake some baseline testing in order to characterise the differences between the electromagnetic diagnostic data that's generated and those that are generated with Coriolis and ultrasonic flow meters. The software tools to actually look at all this diagnostic data are already there. We just have to baseline the differences between the different types of meters. And this is something that we can very simply do on our modernised water test facility.
Yeah. Okay, I've got another one here. If historical data on network bursts and leaks is not available, will it still be possible to develop a software tool to predict leakage with our distribution mains?
Well, as I mentioned with the bunker oil case, we didn't actually have much real life data there because obviously the putting a magnet on a flow meter in a financial account like that is illegal. So we actually use something called synthetic data generation in order to generate the data using a statistical technique. And that synthetic data was then used to actually train and develop the machine learning tools. So potentially we could use the same sort of techniques if we had limited data on historical data where bursts and leaks occurred in water pipelines. So yes, we could still generate a machine learning tool to predict that based on using synthetic data generated by the statistical methods.
Yeah, yeah. And another one, and this is very similar. This one, we often find meter accuracy a problem. We try to do volumetric tests, but as you know, the accuracy is about 3 to 4%. We cannot conclude whether it's a leakage or a meter accuracy problem. The flow meter in question is over a meter in diameter. Um, I guess that's something we can talk to them about, isn't it, Carl? I think this is.
Yeah, well, that's some of the problems that I was in Saudi Arabia earlier this year, and that's some of the problems that they're facing. They have meters up to 2.7 meters in diameter, and there are maybe one or two facilities around the world where you could potentially calibrate that, and it would be hugely expensive. But if it's a modern
Mhm.
flow meter that produce diagnostic data, we could look at that diagnostic data to see if there's any way of predicting, as we did with the Coriolis and the ultrasonic flow meters, looking at the diagnostic data to predict what faults are actually occurring upstream of the meter. So that is a possibility, and that is something that basically the condition-based monitoring tools that I discussed here would be looking at.
Mhm. Yeah. Yeah. Okay. So I think we can probably help you with that issue. We'll get in contact after this webinar. Okay, I think that's about us. There's no more questions that I can see come in. So I mean, really, thanks for joining us, everyone. There's a lot of content to that webinar today. So, as I mentioned earlier, you will receive a link to the recording and the slide deck for today's presentation. Please get in touch with us. Let us know if there's any other webinar subjects you'd like us to cover. It's great to hear exactly what you're interested in hearing about. So, feel free to get in touch with me or send any queries to info.uk@tufsud.com. Please feel free to visit our website, which is tufsud.com/UK. There's plenty of information on there. There's also information on there about other webinars. So if you've got time, have a look through it. You might find something on there that we've already done that you like the look of. And on behalf of myself and Carl, thanks for your time, and enjoy the rest of your day.